So, in this video, we are going to discuss about the Newton's law of cooling. The Newton's law of cooling, the good old apparatus is shown in diagram. So, this is actually the double distilled enclosure with the restrictions of the heat conduction by using the conduction, convection, and also the radiation process. If it automatically just getting into the hot water is taken into the vessel, and the cooling curve is to be determined to that particular surrounding with respect to the time. Okay, so we will discuss in detail in this session. Okay. Well, let us discuss here introductions of Newton's law of cooling and followed by the experimental procedure, theory, and finally summary of the today's idea. Here the one of copy cup is shown here. The copy cup has a temperature around 60 to 70 degrees Celsius. So the surrounding temperature is only room temperature is 30 degree or 23 degrees Celsius. Normally we have to take into the account is 30 degree. So the excess of temperature, the 30 degree, suppose the body, the copy temperature is 60, you try to come to that 30 degree of the atmosphere. So it should, all the heat is to be conducted through the radiation and as well as convection process. So it's a very good example for cooling of the. The statement of the Newton's law of cooling is the rate of cooling is proportional to its excess of temperature above that of the surroundings. Okay. So when the temperature difference between the cooling body and the surrounding is very small, actually the cooling body temperature and that of surrounding, the difference between the two temperatures is very small. The law applies to cooling using convection and radiation, not for radiation alone. Okay. Right. Therefore, we can find out this method to determine the specific capacity of the given liquid by Newton's law of cooling. Therefore, the specific capacity is nothing but if you have to take one ideal quantity that is called 1 kilogram substance. So, how much amount of heat is to be taken into rise that particular temperature up to 1 degree Celsius is called a specific capacity. So it should be one of the very important quantity to calculate the thermal property of the material. So in this aspect, we can using this the Newton's law of cooling method to estimating the value of the specific capacity of that particular liquid by the conservations of heat. But let us take W1 of the empty spherical calorimeter. We can show that the ball-like calorimeter, there is a small hole is there. To inserting the very sensitive thermometer, we can calculate, we can measure that particular temperature of that given liquid at a particular instant of time. Okay, so we got to take W1 weight is to be taken into account. It is filled with water and a temperature of about 85 degrees C. So we can standardize that the particular water is to be using as a standardized liquid. So it should be heated to up to 85 degrees C. The 85 degree, after that 85 degrees Celsius of heat energy, that same liquid is to be filled in that empty calorimeter. It should be suspended in air from the stand. If suppose a sensitive thermometer is inserted into water through the narrow hole in the calorimeter, when the temperature reaches to 80 degrees Celsius, okay, so just wait up to that 80 degrees Celsius, a stopwatch is started. The temperature of the water is noted at a regular interval of 1 minute. Will reaches the water as a 55 degree, the calorimeter is allowed to cool at a room temperature and then waited. That weight has to be estimated as W2. After removing the water from the calorimeter, it is filled with a given liquid that like taken on oil. The oil is to be taken into filled in the given liquid at about 85 degrees Celsius. The temperature of the liquid is noted at a regular interval of 1 minute of the liquid cools from 80 degree. It started that cooling graph at the stopwatch strip started up to 80 degrees Celsius to 55 degrees Celsius. The calorimeter weight content is to be allowed to cool at room temperature, and then weight is to be estimated as W3. So graphs are plotted between the temperature and time. So one is time versus temperature. So we can take the readings from 80 to 55 degrees Celsius for each 1 minute interval of time for both liquids. So you can draw the graph between the two liquids. First one is water and another one is the liquid as oil to be noted on the graph. The time taken for T1 seconds and liquid for T2 seconds to cool from 70 to 65 degrees Celsius. You can estimating the both liquids like water and oil. What will be the time taken to cool? What will be the time taken to cool from 70 to 65? We got to estimate the difference of temperature 80 to 75 to 70 or 55 to 50. So you can estimating the different temperatures. One is fixed as 60 to 70 to 65. From that graph, the T2 by T1 is determined is calculated. But let us have the calculations of that particular idea. Let's see the specific capacity of that galorimeter. Okay. When C1 be the specific capacity of water and C2 be the specific capacity of the liquid, just like our estimations assumed, the assumed things is oil, right? But therefore, the mass of water is nothing but W2 minus W1. W2 is nothing but water plus calorimeter minus the calorimeter weight W1. So W2 minus W1 is the mass of water. And N2 is a mass of liquid, is the W3 minus W1 is nothing but a mass of liquid. Right. So we can estimate the first of all the liquid, the heat lost per second when the calorimeter containing water cools from T1 degree Celsius to T2 degree Celsius. T1 is fixed as 70 to 65. So what will be the heat lost by the particular system like a calorimeter as well as the calorimeter filled with water. Okay, so the first of all we can estimating that M1C1 is nothing but MC theta. The total heat conducted, the heat lost is nothing but MC theta. M is a mass of that particular substance, C is a specific capacity of the substance, and T theta is the difference of temperature from higher temperature to lower temperature within an instant of time t, small t. Okay, therefore this quantity is to be estimated as M1C1 plus W1C into the both quantity is to be rise from the cooling from the higher temperature T1 minus T2, because T1 is a 80 degree or 70 degree, T2 is a 65 degree. But suppose 70 to 65 degrees Celsius is into our calculation. So you take the higher temperature 70 to lower temperature 65. Therefore T1 minus T2 by T1. Small T1 is a time taken to make on T1 to T2. It should be calculated from the graph. The heat lost per second when the calorimeter containing the liquid cools from T1 degree Celsius to T2 degree Celsius, you can return is the same M2C2 plus W1C into T1 minus T2 by T2. Okay, so this is for the second liquid heat lost per second. Okay, so according to our conservation ideas, the same amount of water, the heat lost by the water is equal to heat lost by the oil with respect to 70 to 65 degrees Celsius. So you can equating this both expression M1C1 plus W1C into T1 minus T2 by T1. This is equal to M2C2 plus W1C T1 minus T2 by T2. So from that we can getting that C2 is the specific capacity of the given liquid is calculated as C2 is equal to M1C1 plus W1C into T2 minus T1 by minus W1C by M2. Okay, so this will be a kilogram per actually kilogram per meter squared per Kelvin. So finally, summary of this today's idea is Newton's law of cooling. The rate of cooling is estimated by the Newton's law of cooling idea. The rate of cooling of a given liquid of a body is proportional to excess of temperature to that of surroundings. Actually, the cooling body and the surrounding temperature is to be very small. It should be the heat is to be lost. Heat is to be lost by making the convection and radiation process, not for radiation alone. So, okay, so the coffee cup will be the one of the very good examples of the Newton's law of cooling. Therefore, the on particular time it comes to the room temperature. Automatically, the body, the coffee, the liquid temperature is down to the it come to stability of that atmospheric temperature. Okay, so the heat gained by the substance is via sensitive positions. Automatically, it should be lost by the heat. So it should come to that equilibrium conditions. Okay, so that is called the Newton's idea, Newton's law of cooling idea. So from that we can estimating that particular temperature from 80 to 55. The even each 1 minute it can recording that decreasing of temperature, the cooling of temperature. So from that you can estimating that up to 70 to 65 degrees Celsius, what will be the time taken for that particular liquid as well as water. So you can estimating the from the graph T1 by T2. Okay, so and finally the using this conservation ideas we can estimating the specific capacity of the unknown liquid is to be determined. Okay, so thank you very much for your patient listening.